Hello everyone, welcome to this discussion on UV visible spectroscopy within the molecular spectroscopy series. The UV and the visible region in the electromagnetic spectrum spans over a range of 10 to 400 nanometer for the ultraviolet region, and then above that 400 to 700 nanometer region marks the visible light region, where the 400 nanometer corresponds to the violet color and 700 nanometer to the red color. This part of the electromagnetic spectrum is absorbed by a molecule when it undergoes electronic excitation from the ground electronic energy level to the next higher electronic energy level, that is the first excited state. So the energy difference between these adjacent electronic energy levels corresponds to the energy of ultraviolet and visible light radiations in the electromagnetic spectrum. That is why by absorbing ultraviolet and visible radiations, the molecule can excite electronically from lower electronic energy level to the higher electronic energy level. Here we know that within each electronic energy levels there are several vibrational levels possible, and in each vibrational level we have got several rotational levels. So it is very probable that when a molecule excites electronically from the lower energy level to the next higher energy level, there happens a change in vibrational and rotational energy levels too. So now let's check this possibility, how an electronic excitation accompanies a vibrational excitation. You've got the molecule in the ground state, and the ground state potential energy diagram is demonstrated like this. And when the molecule excites to a higher energy level, the potential energy diagram changes significantly, especially in 2 points. The first one, if you look at the equilibrium distance between the two atoms, that is the bond length, when the molecule excites from a lower electronic energy level to higher electronic energy level, you can see from those two diagrams that the bond length increases significantly. And this difference corresponds to the dissociation energy of the molecule. And if you look for the excited states, the dissociation energy decreased. So these are the two observations when the molecule excites electronically from lower energy level to higher energy level. The first point, that is the increase in equilibrium distance with electronic excitation, reflects molecular vibration, that is the bond length is changing during vibration. So the increased bond length indicate a stretched condition. That means electronic excitation results in a different vibrational status. That means vibrational energy levels change when there is an electronic excitation, and such a transition is called the vibronic transition, that is electronic transition accompanying a change in vibrational level. And such possibility of vibronic excitation is better explained by Franck-Condon Principle. Let's see what the principle is about. It says that the nuclei are much larger than electrons, we know that, and that's why electronic transitions takes place very much faster than the internuclear distance can change. That means the equilibrium distance between the atoms in the molecule when it excites to the higher electronic energy level remains the same, and in order to preserve the distance the same, the molecule should now reach a higher vibrational energy level in the excited electronic energy level. For example, here in this picture, the molecule starts, or in the ground state, the molecule is in the ground vibrational energy level. And when it excited to higher electronic energy level, to maintain the distance, the equilibrium bond length the same, the molecule now enters a higher vibrational level. So you can see a vertical transition preserving the equilibrium bond length the same, although the molecule excites electronically to a higher energy level. And such a transition is vibronic transition with a change in vibrational quantum number occurring due to the electronic excitation. And let's now check the different molecular orbitals and which are the possible transitions allowed. We know that molecular orbitals are mainly three types: bonding, anti-bonding and non-bonding molecular orbitals. The pi and sigma orbitals are differentiated by their symmetries, and always the bonding molecular orbitals are lower energy orbitals than anti-bonding molecular orbitals, and the non-bonding molecular orbitals lie with the intermediate energy. And coming to the possible transitions, the sigma star transition is the highest energy transition, and then follows n sigma star transition. Then you can have pi star transition, and the lowest energy transition is n pi star transition. And it is important to note that pi sigma transition, for example, pi to sigma star transition is a forbidden transition because pi and sigma star, they are having different symmetries. Therefore, the transitions are permitted only across orbitals with similar symmetries. And now comparing the energies associated in each of those transition, you can see that the sigma sigma star is the highest energy transition, then comes the n sigma star with lower energy, and then pi pi star and n pi star with the lowest energy. So for a given molecule, the possible transitions are described by the presence of a lone pair of electrons or pi electrons, etc. So it comes out of the structure of the molecule. And here another point worth noting is that the sigma sigma star transition, the highest energy transition, falls at very high energy region in the ultraviolet region, very low wavelength below 100 nanometers. That is why this very high energy transitions are generally not observed under UV visible spectrometer because it falls in very high UV region. And above that, as this particular transition is found in every molecule, this is not very informative too. That is why people will not generally focus on sigma sigma star transition while studying the electronic spectrum of molecules. Let's now see two examples. The first one I have here is butene. Here let's check which are the possible transitions. Obviously sigma sigma star is possible because there are sigma bonds between atoms, and in addition to that you've got pi bonds which suggest a possibility of pi pi star transition. So for this particular molecule, the dominating character in the UV visible spectrum will be due to the pi pi star transition. Likewise, if you've got this molecule acetone, as before, acetone also has got a double bond between carbon and oxygen. This suggests the possibility of a pi pi star transition. And apart from there, the oxygen atom, this heteroatom bears lone pairs of electrons. And this lone pairs of electrons, since they are occupied in the non-bonding orbital n, it is possible to have an n pi star transition also here in this. This is how you can relate the molecular structure with the spectral features. And let's now see the selection rules for electronic transition. You know that spin multiplicity of the electron is given by 2s plus 1, where s is the spin quantum number. And in this configuration, suppose a molecule have got a configuration like this. Here each electron are aligned opposite to each other. Total spin will be 0 because each of the spin gets cancelled each other. Therefore, if you give s equal to 0 here in this equation, you can see that the spin multiplicity is 1 for this state. That means it is a singlet state. Now when one of these electrons excites to higher energy level, two possibilities are there. First one is like this, that is this particular electron excites to the higher energy level, preserving its spin. That means its spin aligns in the same direction as was before. So the spin multiplicity is again 1, resulting in the singlet state. And the next possibility during excitation is that the electron which excites changes its spin. That is, spin is not preserved in this excitation. So the individual half spins add together to get 1 as the sum, and then 2s plus 1, the spin multiplicity will be 3. That is why this state is called a triplet state. In short, when the electron excites from the ground state to higher energy level, two possibilities are there, one with preserving the spin state and the other without preserving the spin. And the selection rule says the spin multiplicity will not change during excitation. That means a singlet ground state will give only a singlet excited state, not a triplet excited state. So that is about the spin selection rule, that is spin multiplicity should be preserved. And for centrosymmetric molecules, the Laporte selection rule also applies, or the orbital selection rule, that is a change in orbital quantum number delta L should be plus or minus 1. So this is about the selection rule for electronic transition. The spin multiplicity should be preserved, that applies to all molecules, and the Laporte rule applies only to the centrosymmetric molecules. And now let's see how an electronic spectrum looks like. If you plot absorbance against wavelength, you get a peak like this, where the peak position corresponds to the wavelength of maximum absorption, and that is called lambda max. So lambda max is that particular wavelength which is absorbed by the molecule in the maximum amount. Suppose you have got your sample substance on which the given radiation falls with an intensity I0, and this radiation is significantly absorbed by the molecule here, resulting in a very weak transmittance with an intensity I. Then the transmittance is given as the ratio of the transmitted radiation to the incident radiation. And this intensity of absorption is better given in terms of absorbance, which is the negative logarithm of transmittance. Then in the end you get this relation, that is A is logarithm of I0 to I, where I0 is the intensity of incident radiation and I is the intensity of transmitted radiation. And if you have got this cuvette with this dimension measures by L units, that means the path of the light through this cuvette will be L centimeters, let's say. And C is the concentration of the substance kept inside. And now the light falls on it with an intensity I0 and the transmitted radiation intensity is measured to be I. Then according to Beer-Lambert's law, the absorbance is directly proportional to the concentration and path length. And the absorbance can be related to the product of concentration and path length in terms of the constant epsilon, which is called molar extinction coefficient or molar absorptivity. And epsilon is the property of the chemistry of the substance or the chemical structure of the substance. So for a given substance, that means you fix the epsilon, and for the given cuvette, that means you fix path length. Then you can see that absorbance is directly related to the concentration. And we will see the application of this Beer-Lambert's law in quantitative estimation of substances by using UV visible spectrometer very soon. Before that, let's go through the structural features of molecules that give rise to absorption in the UV and visible region. As we have seen before, a double bond give rise to pi star transition, or the presence of a heteroatom like oxygen give rise to n pi star transitions. So these transitions are very pronounced and they give rise to UV visible absorption. Therefore, structures like this, double bonds or the presence of a lone pair bearing heteroatom, etc., are responsible for the absorption in UV visible region, and such structural moieties which are responsible for characteristic absorption in the UV visible region are called chromophores. And there are substituent atoms or groups which can affect the absorption by chromophore. For example, benzene molecule measures a lambda max of 255 nanometer. But in aniline, when you have got amino group as substituent, you can see that this molecule has a lambda max value shifted to 280 nanometers. That means if you compare the two structures, just due to the presence of this amino group, the lambda max values shifted to a higher wavelength. And such groups or atoms or substituents, in short, that causes a shift in lambda max value or shift in intensity of absorption are called auxochromes. And here amino group is an auxochrome which causes a shift in lambda max value to longer wavelength, that is from 255 to 280 nanometer. And on contrary, you can also see that when aniline is protonated, this particular ion absorbs at lower wavelength, that is 203 nanometers. So you can see two different kinds of auxochrome activity. That is the first one shifting the lambda max from shorter wavelength to longer wavelength. Such shift is called bathochromic shift or red shift. And the second one, like in protonation of aniline, that is shift in lambda max to shorter wavelength. Such a shift is called hypsochromic shift or blue shift. Here in bathochromic shift, lambda max value shift to longer wavelength like the auxochrome NH2 does in case of aniline in comparison to benzene. And hypsochromic shift is shift to shorter wavelength like in protonation of aniline. Here proton is the auxochrome. And another possible consequence of auxochrome is shift in intensity of absorption. That is, absorption intensity can be shifted to higher value as reflected by the epsilon value, and such a shift is called a hyperchromic shift. And here you can see in this example, pyridine absorbs with an epsilon 2750 units, and when it is methylated at the second position, the intensity of absorption increased with a higher epsilon value 3560. Such a shift is hyperchromic shift. And the opposite can also happen there. The intensity of absorption decreases due to the presence of auxochrome, and that is called hypochromic shift. Here in this example, you have got naphthalene absorbing with epsilon value 19,000, and in methylated naphthalene, you can see it is merely above 10,000. So this difference in epsilon values, or in short the difference in intensities of absorption, is called hypochromic shift. So in short, an auxochrome can have influence both on the lambda max value and on the intensity of absorption, and lambda max is changing either in bathochromic shift or in hypsochromic shift, and the intensities are changed either as hypochromic shift or as hypochromic shift. And now let's see some of the structural features which contribute to the absorption in UV and visible region, that is some of the chromophores. Here for example, a carbonyl group present in a molecule give rise to N-pi star transition and pi-pi star transition due to the presence of this pi bond and the heteroatom bearing a lone pair of electrons, and the lambda max value due to this particular structural moiety is around 280 nanometers. Like this, you can see different chromophores and the respective lambda max values. And it is very interesting to note that you've got conjugated diene here, that is double bonds placed at alternate positions, and here you've got only two double bonds. And the lambda max value for such a skeleton is around 233 nanometers. And in the conjugated triene, that is when you simply add 1 degree of conjugation there, your lambda max is now 268 nanometer. So if you compare the conjugated diene and triene, you can see that just by the addition of one more double bond which extends conjugation, you have an increase in lambda max by around 30 units. And the same you can see for conjugated tetraene, where there is one more double bond added with an increase in conjugation, then the lambda max value again increased by 30 nanometers. So this observation is there, that when you have got addition of a double bond which extends to conjugation, the lambda max value shifts by around 30 nanometers, and such observations are concluded in Woodward-Fieser rule. And before coming to that, let's see an interesting observation of highly conjugated natural molecules like in pigments. Here you've got carotene, the pigment present in carrots. Here you see a highly conjugated system. So as seen before, as the degree of conjugation increases, the absorption shift to longer and longer wavelength, and with this much degree of conjugation, the absorption shift to the visible region, so they are colored. And now let's check the Woodward-Fieser rule. It says that for a heteroannular diene, that means the double bonds are present in separate rings, then the base value will be 214 nanometers. And on the other hand, for a homoannular diene where the double bonds are present in the same ring, the base value will be 253 nanometer. And here shown are the increments due to the presence of additional structural features. That means if you've got a double bond extending conjugation, the lambda max will be shifted 30 units. That means suppose I have got a double bond over here, this extends the conjugation by one more degree, then the lambda max will be shifted 30 nanometer to the right. Likewise, an alkyl substituent adds to the lambda max by 5 nanometer to the right, and a secondary amino group for example adds by 60 nanometer, etc. So in this way, you can predict the pattern of a UV visible absorption spectrum or the lambda max value for the given molecular structure. And such a consolidation comes under the Woodward-Fieser rule. And at this point, I am not going to the details of the application of Woodward-Fieser rule. But now let's have a look on the basic parts of a UV visible spectrometer. Here is how a UV visible spectrometer looks generally, thanks to the web page of CamScope for this image. And the major components of the instrument are a source of the light, can be a tungsten lamp or a deuterium lamp, and the radiations passing out of the source are passed through a monochromator which selects the required particular wavelength, and then it is split into two, and the one part is going into the sample cell and the other part to the reference cell, and after absorbing, the transmitted radiation is collected by a detector and it is analyzed by an output unit like this. And one of the important applications of UV visible spectroscopy lies in quantitative analysis of materials based on Beer-Lambert's law. Here for example, in the first test tube you have got a solution of iron and you want to estimate the amount of iron present here. You are making it to react with the thiocyanate iron and the product will be a red blood colored solution. And this red blood colored solution absorbs in the visible light region with a lambda max of 480 nanometer. And so, before proceeding with your unknown sample, you need to prepare a set of calibration standards of known concentrations of iron, and these solutions are made to react with the thiocyanate iron to get the colored solutions. And then all these colored solutions of known iron concentrations are brought under UV visible spectrometer to measure the absorbance. And you know that according to the Beer-Lambert's law, as you are using the same Q weight, you have got L fixed in all the cases. And as you've got the chemistry of the iron same, that means all are iron thiocyanate solution, then the epsilon will be same throughout. Then the only variable is concentration. So when you plot the absorbance against concentration for the standard, you get a direct relation, a linear graph is obtained. And now you measure the absorbance of your unknown sample, which is converted to ferric thiocyanate solution. And suppose that your unknown absorbance lies at this value, then by extrapolating to the concentration axis, you can know the unknown concentration of the given solution. So this is how you use UV visible spectroscopy to estimate the amount of substances quantitatively. So in the first step, what you can do is, if the original compound is not absorbing in UV visible region, you can conduct reactions and convert it into a compound which is absorbing in UV or visible region. And then a set of standards is prepared, their absorbance is measured to get this calibration plot, and just by the measurement of absorbance of the unknown sample, you can get concentration from the graph. This is the procedure. And exclusively for colored compounds where you know the lambda max values, you can use a simpler device called colorimeter, which measures the color, the intensity of the colors. And the application of UV visible spectroscopy lies in quantitative analysis, as we have seen for environmental samples. For example, if you have got a water sample and if you want to estimate the amount of iron inside, or primary nutrients such as nitrate, phosphate and sulfate, and the structural characterization of synthesized organic molecules and detection of conjugation in molecules and presence of impurities can be detected by UV visible spectroscopy. And the most application of this technique lie in environmental and pharmaceutical industry for qualitative and quantitative analysis. And the biggest advantage of the technique is that it works for very low concentrations. For example, for your estimation of iron in the given solution, colorimetry techniques can be used in case your volumetry techniques fails because of the concentration limit. And it works for any species like atoms, ions and molecules, and you can investigate selected species from a complex mixture of substances because the lambda max value is specific for a given compound. The solvent effect is eliminated because you are using a reference mostly, and the method is almost non-destructive. So in most contexts, you can reuse the substance. That's all for the time being with UV visible or electronic spectroscopy, and the next big thing to come up is NMR spectroscopy, the nuclear magnetic resonance spectroscopy. Thank you.